as he was just telling me over lunch, every time ASML sell another EUV lithography system, Tokyo Electron Limited celebrates as well, because as I'm sure you found out from your pre-class assignment, they very much provide a huge part of the ecosystem necessary to make use of those systems. And in fact, one of your units is actually inside the EUV machines itself as well, is that right?
Yes, that's actually.
So I'd like to introduce Rinus Lee to come tell us about TEL and their work. Thank you very much, Rinus. Over to you.
Oh, all right. Thank you. Good afternoon, engineers. Good afternoon, engineers. Come on, can you give me a little bit of energy here? Okay. So it's really a great pleasure to be here at Purdue. This is actually my first visit here to Purdue. I've worked with many Purdue alumni, but I have never actually visited a faculty. So thank you, everyone. Thank you for the organizing committee to bring me here to share with you some of the things that we do at Tokyo Electron, and what are some of the opportunities for engineers like us to work in the semiconductor industry. So my name is Rinus. So I'm a process engineering manager in Tokyo Electron. So I worked in the development facility here, not here, at Albany, New York. So a little bit about myself. So like what I mentioned, I work in the TEL Technology Center in Albany, New York, and I worked in the Thin Film Process Technology Division. So a little bit of background about myself. So on the picture on the right, does anyone have any idea which city is this picture? Great, yeah. So I'm originally from Singapore. So I spent the last 15 years in the US working on at different technology companies. So here is a little bit background, a little bit about my background and industry experience. So you could see on the upper left, I did my PhD, MS, and BS, or Bachelor of Engineering, all in electrical engineering itself before I joined the semiconductor industry. So as I went through the industry, I shared with some of the students that were in a networking session. I had the good opportunity or the pleasure of working in different sectors within the semiconductor industry itself. So you could see I started my career as a process integration engineer, working on high-K metal gates, FinFET, and exploratory device technologies, which I think some of you are aware from the classes that you took. Thereafter, I went into process engineering. In this particular field itself, I look at more the development of the unit process, such as laser annealing, ion implantation, and metallization. And finally, before I joined Tokyo Electron, I had the pleasure of working actually as a device engineer in RF engineering. So what you could see here is I had the opportunity to really work across a breadth of disciplines within semiconductors itself. And I was told to share a little bit about my career path. So like many of you are thinking, what would you do if you choose a career in semiconductors? So, to get a feel whether I wanted to be in semiconductors, I took up an internship, and I did my internship at TSMC in Taiwan. So I spent 6 months there really looking at the different processes that they have, how they work in the semiconductor industry, how is the culture like within a semiconductor industry itself. And that really solidified my desire to join this industry. Right after graduation, I was able to move to Germany. I worked with a company called Robert Bosch. It's a integrated device manufacturer, so which means we do everything from design, manufacturing, and the device itself. Subsequently, from Germany, I had the opportunity to move to Austin, Texas. It was a role that came up, because they were looking for new engineers at their facility in Austin. So why not? From Singapore to Germany, I decided to move to the US. So the rest of my career, basically in the US itself, at various technology companies from Semitech, Global Foundries, and now I'm at Tokyo Electron, based in Albany, New York. So I was told to share some, nuggets of information or, fun facts. So these are two things I always think about for ingredients for success. Vision without execution is really hallucination. So that is something I keep in mind, in my career itself. We have a lot of ideas, but we really have to execute on these ideas to really make things work, make things happen. And this is what we do as engineers. So do remember that. The other thing is, when I look at all of you and the networking session I had with the students, it really inspires me because you are the new generation that's going to come after me, that will come with this new thinking that help us solve these problems that we have created or these problems that are existing. So like what I've written here, we cannot solve our problems with the same thinking. It needs thinking from you all that are coming to join us in the industry to solve these things itself. A little bit more fun fact about myself is I really enjoy backyard astronomy. And I'm really a big fan of LEGO itself. And you could see here, I could merge my two hobbies itself, backyard astronomy with LEGO. And you could see here is a Hubble Space Telescope made from LEGO itself. So moving ahead, since I'm giving the last class today, I think I had the pleasure of just recapping the current trends and the outlook of our semiconductor industry. I'm quite sure the various speakers before me have shown you the trends and the outlook of the industry itself. So I'd like to really cap off this class by reminding or going through this again. So shown here is really the history and the future of the semiconductor industry. The industry started in 1947 with the invention of the transistors. And then for my career, I grew up in the 1990s to 2000s itself, so it's really dominated by the PC-centric and mobile-centric technologies driving the semiconductor industry, the computing itself, the mobile phones itself, which became ubiquitous, with technology itself. And I think most of you are in this data-centric era where you're growing up, going to school itself, all the apps they're using on your phone, all the different softwares they're using online are all really driven by this data-centric burst in terms of technology that's driving the semiconductor industry. And of course, you are really familiar with, in the 2020s and the future beyond, AI-centric sort of workloads are really, front and center driving the semiconductor industry. And as we move in the future, of course, generative AI, autonomous driving, and virtual reality are really going to be big drivers of the industry, as you could see in the next page. So what does all that growth really translate to? So this is the semiconductor market that's projected to reach $1 trillion by the time 2030. 2030 is just a couple of years away from now. So you could see from this chart itself, we are, given the projection in 2022, we are about a $500 or $600 billion industry. So we're going to double in the next few years to $1 trillion. So what does this really all mean for us? It means we need more semiconductors. So what does it mean when we need more semiconductors? Could anyone give a guess? How do we have more semiconductors? What do we need to do to have more semiconductors? Yes?
Increase production?
Yes, that's right. So we have to increase production to allow us to have more semiconductors to drive the industry to $1 trillion. So this chart really shows what we need to do. So this is a chart by SEMI. You could see the fab production expansion capacity from 2022 to 2026. So on the left itself in the Americas, the blue circles are for the 300 millimeter fabs, and the green circles are the 200 millimeter fabs. So you could see across worldwide, it's projected there will be 94 new fabs itself, with 18 fabs in the Americas, 13 fabs in Europe, and about 60 over fabs in Asia itself. So you could see this is a really expansion of what we need in terms of semiconductors or meet the production capability. So why is this so? Because you could see here, semiconductors is really pervasive in all technology. I think last class you had someone from Medtronic coming to give you a class. You could see semiconductors is in healthcare. Semiconductors is in retail. Now with the Amazon Go itself, you're checking out without going through a cashier. These are all enabled by semiconductors. Without semiconductors, all these industries will not be how they are today, even for financials, architecture, and construction. So this really drives home the message. Semiconductors touches every aspect of our life. So how do we drive this innovation of semiconductors itself? So you could see here is a slide of the research and development expenditures as a percentage of sales here. So you could quickly see that among all the major industries, of course, pharmaceuticals and biotechnology drives about 23% of their sales into R&D, but semiconductors follow closely at 20% itself, which indicates to you the amount of challenges that we have, the amount of know-how that we need to do to be able to expand our industry, which is why the semiconductor industry is devoting almost 20% of our revenue to semiconductor research. But if you take a closer look, semiconductors have been split into semiconductors and semiconductor equipment. So if you think about it holistically, we as an industry, we're actually spending close to 30% of our revenue on R&D itself, which is substantially more than even pharmaceuticals and biotechnology. So what does TEL or Tokyo Electron play in terms of the electronic business food chain? So you could see here, this is a chart showing the worldwide market for electronic systems. And like what I showed earlier, the semiconductor market is worth about $500 billion right now. So if you remember, I mentioned that our industry is going to $1 trillion. And here you could see TEL participates in the wafer fab equipment market. So in the next few years, this market is going to go from $100 billion to $200 billion, which is a significant market that available to the wafer fab equipment suppliers. So now let me introduce TEL a little bit. So maybe a raise of hands before this talk or the pre-lecture notes that you read. How many of you are familiar with TEL? How many of you familiar with TEL knows which market we participate in? Great, yeah, so a couple of you, yeah, great, thank you. So let's look a closer, to TEL. So Tokyo Electron, by the name, suggests that we are a Japanese-based company. We are based in Tokyo. Our headquarters is there, but we are a worldwide organization. You could see our operations is throughout the world. Anywhere you find one of our major customers, you'll see us. You could see on the left itself, we are found in Europe through various head offices or branch offices. And of course, in Asia, we have multiple sites throughout, China, Taiwan, Malaysia, and Singapore. And of course, in Tokyo, in Japan itself, we have most of our head offices and development centers throughout the entire entire Japan. And here in the US, we have a couple of facilities. You could see there's a TEL Manufacturing and Engineering of Americas, where we do a lot of hardware development. And there's also the TEL Technology Center of America. So this is the organization where I come from, or I belong to. So this is based in upstate New York, where we do most of our process technology development to enable our customers to build their next generation of chips or technologies. So you could see here, we could be found in 19 countries, and we have a total of 87 sites across the world itself. So in a nutshell, what Tokyo Electron does is we develop, we manufacture, and we sell the tools that build these computer chips or these semiconductor chips that our customers such as TSMC, Samsung build. And by doing this, we enable life by this technology itself. So let me run through a little bit the history of Tokyo Electron. So we were established in 1963, first as Tokyo Electron Laboratories, based out of Tokyo itself. And in 1978, we rebranded to Tokyo Electron Limited, which is now we are known as since 1978. So throughout the years, we have been recognized by various organizations. For example, in 1991, we are the top sales among all semiconductor production equipment manufacturers. 2018, we are one of the top 100 technology leaders in the world. And 2021, we are recognized as one of the most honored company for the 6 years in a row itself. So these are different innovations or different awards that we have received over the years as a company, collectively driving technology. So what do we really do? So shown here is a snapshot of the semiconductor manufacturing process itself. So let's start by the first on the upper left itself, which is really deposition. So in this particular step, we put down materials onto the substrates or the wafers itself, such as metallization films, dielectrics. Once we put down these metal films, the next step is really lithography, where we make these patterns. So like what was mentioned, lithography is enabled by ASML, but for every ASML tool, there's always a TEL track where it supplies the wafers to the EUV lithography tool. Because in lithography, you have to have resist, you have to bake the resist, and this is what the TEL tool does for the lithography systems itself. Then after developing the patterns, of course, we have to define these patterns, which move on to the next stage, which is etching. So TEL has a pretty big market share in terms of etch tools. So this is a particular step where we define the different features in the devices itself. You could see, now we are starting making patterns on the structures itself by doing the etch. So after the etch, the next step is really to clean up the wafers itself. If there's any residues or there's any polymerization of the different structures itself. So you could see here, it goes through the wet cleaning process with different chemicals by etching and cleaning. So you could see, for example, it's shown here, there's these gray wiggly lines as the resist. So after doing the etch, the resist is still on top of the film. We have to remove the resist by etching or by chemical cleaning itself. So once we've done that, it goes on through the manufacturing process down to the interconnect formation. So now you have the patterns or you have the structures. How do you connect these structures to electrically testable? So this is basically the next step here, where we do interconnect formation, where we have a lot of tools in terms of ALD, CVD, where we put down the different high conductivity metals itself for interconnection. And finally, of course, after the formation itself, we would require testing. So these testing includes wafer probe level, chip level probing of the test chips to verify whether these are all feasible or these are working dies itself. And finally, we go on to packaging itself. This is an area that has received significant interest from the industry itself, because packaging is where there's a lot of new development happening. For example, shown here is just the wafer bonding and debonding, where we put two wafers together to try to stack the devices or stack the chips together to gain more functionality for the same footprint itself. So this is where Tokyo Electron participate in the whole semiconductor manufacturing process. We provide the tools and equipment to the foundry customers to be able to make the different chips or technology they are making for their customers, such as Google, Qualcomm, and so on. So how do we drive all this innovation? So this innovation is really driven by the TEL Research and Development Centers. Our research and development centers are worldwide. So once again, you could see here, this is the worldwide map. We have a lot of operations or development in major customer sites. For example, in Taiwan, we have a technology center. We work closely with our Taiwanese customers. In Korea, in the same way, we have a technology development center working closely with our customers, delivering solutions to them so they could manufacture the chips that they are tasked to do so. Here in the US, like what I mentioned previously, we have a couple of locations, but specifically for process technology development, most of it is done in the TEL Technology Center in America, where I am based. And for TEL, we have a headquarters in Austin, Texas, where we do a lot of modeling, simulation, and plasma simulation sort of work. So shown here is the TEL Center of America. This is based in the Albany Nanotech campus. This is a facility that belongs to the New York State, where they have multiple companies coming together to work on different research projects or development projects itself. So shown here, this is based in upstate New York. So you could see there are multiple fabs in this facility here. Tokyo Electron occupies one of the buildings here. We have about 200 to 250 development engineers based in this location. And you could see there's further expansion that we are building another fab here in this location. So like what I mentioned, this is the largest technology development center for TEL here in the US itself. So here, the next few minutes, I'll show you what happens within the fab itself, an industrial research fab, where companies do their development. So this is a video from the New York State itself, and let us start.
Pretty cool stuff, right? I'm Dave Anderson, president of the New York Center for Research, Economic Advancement, Technology, Engineering, and Science, or New York Creates. New York has always been at the forefront of innovation. It's in our DNA. Today, along the same path as the Erie Canal, we've built a thriving semiconductor ecosystem from Albany to Buffalo that will power the next generation of technology. In fact, there's a good chance that the technology of the chip that's inside the device that you're watching right now was developed here 5 to 7 years ago. We're going to give you a tour of the Albany Nanotech Complex, where $15 billion in investment has created America's largest and most advanced semiconductor R&D facility. This site has over 1.6 million square feet, so you're going to get some steps in.
Hi, my name is Christopher Gorst. I manage operations and technology here for New York Creates on the Albany Nanotech Complex. We're here in front of our NanoFab East building, the main entrance to the Albany Nanotech Complex. Thousands of visitors per year come through these doors and through this rotunda in order to participate with us in our research activities on site. Here we are in the link between NanoFab East and NanoFab South. It's one of the many links on site that connect the rotundas. NanoFab South is one of the earliest buildings on site. It houses many of New York Creates industry partners, including Tokyo Electron. Their TTCA is the largest technology development center for the company within the United States. We're here in the Albany Nanotech NanoFab South facility, where we use 300mm equipment to bond wafers, dice wafers into chips, and stack those chips together. I'm I'm standing in front of a piece of equipment that performs testing on our chips and wafers to determine whether our experiments were successful or not. If we made the technology smaller, faster, and better, these e-test systems tell that to us. We're here in NanoFab South Annex. This fab performs some of the earliest steps in the production of these test chips. The piece of equipment behind me is used to make some of those metallic connections using the C4 process, which stands for Controlled Chip Collapse Connection. This corridor connects NanoFab South Rotunda to NanoFab North Rotunda. It was built in 2004 to connect those first two buildings on site. Since then, we've built NanoFab Central, and access to that clean room is provided through this hallway. I've just entered NanoFab Central through our main gowning area. We apply these gowns, hoods, and gloves in order to keep particles off of us from interfering with the chips, devices, and wafers that we produce in our prototyping facility. NanoFab Central is one of our most advanced 300mm clean rooms. It's approximately 20,000 square feet of our 150,000 square feet of clean room on site. We use that capability to perform joint development in advanced semiconductor research with our industry partners. When NanoFab Central was built, it provided a connection to NanoFab North, which added approximately 20,000 square feet of clean rooms. This is NanoFab North Clean Room. It's one of our largest clean rooms in the Center for Semiconductor Research. It contains approximately 50 state-of-the-art 300mm pieces of equipment that help us generate today's prototypes for tomorrow.
So I hope I gave you a good sense of how a leading-edge semiconductor fab works here. So I'm going to stop this video because it runs for a few more minutes. So I've introduced you to Tokyo Electron. I introduced you to how, what looks like within the fab itself. But what do we really do? So the next few slides, I'll just touch on a little bit about the technology trends for the advanced logic devices and some of the process technology that we develop and why is it important for advanced logic devices. Shown here is a generic logic technology roadmap. So you could see here, these are just the schematics here just represents the different device architectures that is projected to be introduced into the industry. So currently, at the 3 nanometer technology node, the device architecture of choice is FinFET technologies. So as we continue to scale our technologies, there are different device architectures that come into play. So you could see the FinFET has the vertical fins here. These are really the channels where we get our drive current of these transistors. But as we continue to scale these transistors, you start to notice there is so much you could scale a particular fin itself before we run out of our critical dimensions. So what the engineers or the device engineers are thinking, why don't we now stack it in this horizontal manner? So you get a lot more fins in the vertical direction. This allows us to have more drive current itself. And of course, as we go forward, we will continue scaling. But once continue scaling, we run into some roadblocks. There's only so many fins so many nanosheets we could put in this direction. There's only so much scaling we could do in this direction. So we are thinking about why don't we stack the PMOS on the NFET, or the PMOS on the NMOS, or the NMOS on the PFOT in this sort of structures itself. So you could see the industry is always innovating on the different device structures that we need to drive the industry forward. And if you look far ahead enough in 10 years or even beyond, we are thinking of replacing the silicon channel with alternative materials such as 2D material stack, which a lot of your professors here actually start working on so that it will intercept what the industry needs in 10 years' time. So what does this really all mean for process control? So you could see I showed the different device architectures. They are all in different directions now. So the traditional way of depositing the materials were directional. It's no longer possible on these advanced structures. So what we really need is angstrom level process control. And what do I mean by that? So the next few slides is really introducing you all to atomic layer deposition using a very simplified schematic. So this particular technique is widely used in the industry for a lot of different deposition because it's conformal and it's also highly scalable. So you could see here, typically this process starts with the sample surface or maybe your device structure being treated or functionalized. So after functionalizing this surface, the next thing we do is we have a chemical A, or we typically call it a precursor, flow into the chamber itself, or we typically call it a pulse. And then this chemical A, these green triangles, will react with this sample surface here, forming some sort of a reaction. What happens next is, by forming a reaction with this sample surface, of course there's some byproducts that's going to be generated, denoted by this pinkish green triangles. So further on, the sample surface eventually will be saturated because all the chemical A's will be on this surface itself, and there's no longer any site for chemical A to land on the sample surface. So this saturates and forms a monolayer on this surface itself. But what do we do with the remaining chemical A and byproducts within the chamber? So at this stage, we flow an inert gas, typically like argon or nitrogen, in these blue circles. We flow it in, and then we pump it out of the chamber, removing any remaining chemical A or byproducts itself. What we do next is we introduce another chemical B, and then it's flow into the chamber again, and it reacts with the surface. And the surface this time will be chemical A. So by reacting chemical A and chemical B together, we could form different sort of films that we want. It could be an aluminum oxide, a tinitride, depending on the chemicals that you choose. So by doing this chemical A and chemical B rotation, you could see once again chemical B, orange shapes coming down onto the surface, react with the chemical A. There will be byproducts generated. And then similarly, when enough chemical B comes down to the surface, it will just self-saturates because there's no more sites for chemical B to react with chemical A. And then similarly, we will introduce the inert gas and bring out all the remaining chemicals. So you could see here what happens is by reacting two chemicals together, we have a monolayer of a dielectric film or a metal film, typically about 1 or 2 nanometers in thickness itself. And by doing this in a sequential manner, by pulsing, purging chemical A, pulsing, purging chemical B, you could start to increase the thickness of the films that you want. And this is in a very controlled manner because there's no way for chemical A to grow any thicker than the sites that are available for it to react. So what I'm saying again is, for example, chemical B, these are all the sites for chemical A to react. So when chemical A comes down, it will just react with all these sites, and once they are all passivated or reacted, any more chemical A coming down would not react, so the thickness will not increase. So this gives us angstrom level process control without sacrificing precision. So like what I mentioned, this pulsing and purging is a cyclic motion depending on the thickness that we want, and then finally we could get to the desired outcome that we want using atomic layer deposition. And what are the applications of atomic layer deposition? So here are a couple of TEM micrographs of how atomic layer deposition is used in the industry. So on the left is a couple of different structures. So let us focus on the structure on the upper left. This is actually a cross-section of the FinFET. This is the fin itself, and then we have this oxide and metal layer over this particular structure. By using atomic layer deposition, you could conformally deposit these layers surrounding this particular structure. If you are not using atomic layer deposition, for example, you are using a directional deposition method, which means the reaction with the surface is not self-saturating, you would not be able to get the film conformally on this surface, because you could imagine, let's say you have a deposition technique with your material coming down in this direction itself. So it will just land on these directions, and of course it will land on the side of this fins itself, but it will not be in such a conformal manner, which means it will not be such precise process control in terms in the angstrom level. So the next few are just examples. For example, this is a nanowire sheet. So you could imagine if we use a directional deposition, the metal or the particles will come down this way, which means you have deposition on this side, but not on this side itself. But by using atomic layer deposition, because it's reacting with the surface, so this is the entire surface. As long as the chemical comes in, it will react with the surface, therefore forming a film itself. So you could see in this example, it's forming a aluminum oxynitride and a hafnium oxide itself by self-saturating. So this definitely gives us a lot of control over these advanced structures. And on the right is a device structure by IBM showing the 2 nanometer nanosheet transistor. And you could see once again, these are the nanosheets itself or the channels. How do you fill these areas between the channel? So by using atomic layer deposition, by reacting with the surfaces, you're able now to fill these surfaces that wasn't possible with directional deposition. So I'll introduce you to an atomic layer deposition process control, which is critical for the semiconductor manufacturing. But what is the future of semiconductor manufacturing? Here is a 1 minute slide, 1 minute video, which I'd like to share with you what we are thinking in terms of advanced semiconductor manufacturing moving forward. So that's all. There's a lot of things will be automated, digitalized. I think in the earlier networking session, there was a student asking what could a robotics engineer do in Tokyo Electron itself. So you could see in the One Touch startup where we have robots coming in to assemble the equipment itself. So everything is in a plug and play format. So there's a lot of innovations that are happening at the future of semiconductors. So all disciplines, whether you're an EE, Chem E, or material science, you are all welcome to participate in this future of the semiconductor itself. So to tie it all back in, so what does it really mean for you engineers that are coming to the industry in the next few years itself? So here at Tokyo Electron, we have a lot of internship opportunities available, and a lot of internships are turned into full-time positions here at Tokyo Electron. So the next slide is just an example of some of the success stories that are at Tokyo Electron. So on the top left is Jack Rogers. I work with him closely. He was an intern with us in 2020, and then after graduating with PhD, he joined us as an integration engineer at the same development facility I worked with. And currently, he's actually on a long-term expat assignment to Japan for the next 2 years. So you could see coming in from an intern, he had a full-time hire. Now he's on an assignment to Japan itself. So the opportunities in a global company is just limitless. It depends on what you want to do. And this is on the technology space. The other intern that we have, Sophia, she actually did her master's with us, and she did an internship in 2018 on the technology side of things. She was working actually with thin films technology, which is the division I'm in. But after graduation, she wanted to work on the more business side of things. So we actually joined the product marketing engineering group to leverage on her technical skill, but looking at how business, for Tokyo Electron, how I interact with our customers, business projections and things like that. So I just wanted to highlight, how internships at Tokyo Electron really turn into full-time positions and what are the different opportunities within Tokyo Electron. So with that, I'll end this with this last slide. I think in the fun fact that was chosen, I chose engineering because I wanted to turn science into applications, because I want to make a tangible impact to society. And when I joined Tokyo Electron, this was the corporate message, and it somewhat resonated with me because of what I chose to do engineering in the beginning. The message here is, yes, technology enabling life is TEL, T-E-L, but the essence here is really we are developing technology, enabling life. Every aspect of our life is driven by technology. So I'd like to end with this. Thank you for your attention.
Thank you very much. Now, who would like to ask the first question, or should I grab one off the sheet to start with? So, of the questions submitted already to the There's a question about the kind of improvements you've made to support the new high NA EUV machines that are starting to be shipped to folks like, I believe Intel might have the first couple of them.
So for the high NA EUV systems, of course, those are manufactured by ASML. We are not involved in the actual development of the tools itself. But like what I mentioned, the CleanTrack system, which is attached to the EUV systems, are all supplied by Tokyo Electron. So because the lithography involves resist, revolves around baking of the resist, so that's what we do. So to enable high NA itself, the resist needs to be thinned down because of the resolution of the high NA EUVs itself. So that's something we are working on, how to generate the next generation of resist that's compatible on tool that could be used in these high NA EUV tool systems.
Thank you very much. Anyone else? Oh, sorry about that.
So as a process engineer with Tokyo Electron, what are the challenges that you have? If most of your production is in Japan and off-site, what's the challenge between connecting the results that you have as a process engineer to actual industrial output?
Okay, so that's a really excellent question because, you know, as a headquarters in Japan, a lot of the hardware engineering and also process engineering happens in Japan as well. But you could see in the worldwide R&D map, which I showed you, tell us across the world itself, different technology centers, and the one that I belong to is actually one of the largest, or the largest in the US itself. So how do we define the different, you know, R&D activities? Is for example, here in the technology center I'm involved with, we have a lot of EUV tools, which might not be available in Japan itself because a lot of the EUV tools are within the customers like Intel, TSMC itself. There are only 2 available sites worldwide with publicly available EUV tools. One is in Europe at IMEC and one is in New York State in the facility I work in. So to answer your question, a lot of the process technology development that we do in the New York State is based around the EUV itself. But of course, we do work a lot of different process technologies and we work with our partners in Japan, what makes sense to do in Japan and what makes sense to do here in the US. For example, maybe at Purdue, there is a really excellent program on a particular topic that it makes more sense to do this in the US than in Japan and vice versa. So that's how we, you know, differentiate what projects gets done where and, you know, how we interact with our counterparts between the US and Japan.
So while we're waiting, there's I guess a kind of related question, which was how does TEL communicate with semiconductor manufacturing companies to identify the new capabilities, the equipment that they'll need?
That is really, really excellent because in Tokyo Electron itself, we are also asking our questions there because we used to be able to do silo development. Our customers do their own development, we do our own development, material supplier do their own development, then we come together. But as the technology becomes more complex, we have to engage at a much earlier stage to understand what are the requirements of our customers, why do you need this material, and how do you integrate this material. So to counter that challenge, we start way beginning by shifting all our development to the left in terms of timeline itself, so that we could collaborate at the initial state of the ideas, what is needed, so we could, you know, come up with ideas that, you know, drive these innovations.
Go for it again.
Yeah, so to continue down that line, as the process engineering manager now, in your role, how do you kind of set the tone for future developments? Do you get kind of a technology overview, like a future state overview from your managers, or on your side, do you have certain objectives that you assign your engineers to, and it goes on a quarterly rotation?
Yeah, so every year there will be some sort of strategic planning on the, you know, high value problems that we should look at, and then it's cascade down to the different levels itself. So for research projects itself, there's general directions or, you know, technology inflections all companies work on. So maybe to take the example of the EUV itself, we know that this is a major technology inflection as we go from EUV to high NA EUV. So with that defined, so we have an overall direction, then we will define the different work packages that's needed, what makes sense to, you know, continue to drive the business for Tokyo Electron, or what doesn't make sense to do, because for EUV or the surrounding work around EUV, there's just so many things that to be done, but not everything has to be done by Tokyo Electron. So it's through this strategic planning, the projects come downward, and then when it cascades to my team, then we would discuss as a team what makes sense, what resources and what expertise we have. And if we don't have the expertise, do we hire another engineer that has the expertise to join us, or we self-develop this expertise by doing further research and development? That's how we generally tackle the different research problems or research topics we have at Tokyo Electron.
So another question we had on a kind of slightly larger ecosystem level was, as Tokyo Electron Limited is in some ways a Japanese company, how does that interact with the CHIPS Act funding that's affecting the United States and so on?
So for the CHIPS Act funding here, so a lot of our partners are participating in that CHIPS Act itself, getting funding for their facilities or for their development projects. So as Tokyo Electron, we would partner with them to support their work in this CHIPS Act itself. So for example, like Intel has a big funding from the CHIPS Act for their new fabs. Of course, we are supplying a lot of the tools, the new process technology to them. And recently, New York State won the NTSC High NA EUV Center. With that, we will support a lot of their work with our with our clean tracks, with our engineers. So that's how we work with our partners that have won the CHIPS Act funding itself.
Thank you.
I actually have a question for everyone here. I'm really interested to know how many of you are thinking of pursuing a career in semiconductors, or actually taking majors that would, put you in trajectory to do semiconductors. Wow, this is really encouraging. You made my trip worthwhile to see so many of you doing semiconductors. Yeah, thank you. I'm really encouraged by this, because a lot of times we have like I showed, we are building 94 fabs in the next few years itself. Where are we finding that engineers? Engineers are here, so I'm really encouraged by so many of you are interested in semiconductors itself.
Question about your current products. How long do you expect those to be in use before they might become outdated or a new technology comes around to replace those? Or do you try to design flexibility into your products to make them last through like future technologies?
So a lot of the work that we do, or the semiconductor industry does, last through generations. So for example, I showed you we are marching to 2 nanometer, 1 nanometer angstrom level technology itself. But during the pandemic itself, I think a lot of you are aware of, there's a shortage of cars. And the shortage of cars was driven by the shortage of semiconductors. But those semiconductors are really legacy semiconductors. Those are like 40 nanometer technology, 65 or 95. So those technologies are still running, process technologies that we developed 10, 15 years ago. So in short, the technologies we develop would always be used until that technology is no longer in production. And for new technologies, you could see in the chart where I showed the advanced device technology progression, you could see it changes every few years. So what I'm saying is we have way too much work to do, because every 3 years there have been new process technologies are needed to enable these new device structures. Yeah.
So I've noticed that a lot of people work, relating back to your question, a lot of people that work in semiconductors have like a graduate degree. Do you think that given like the demand for semiconductor, that maybe there won't be as high a percentage of maybe workers that have a graduate degree and more just a bachelor's degree? Do you think that's a trend that you will see?
I think it's probably a misconception to work in the semiconductor industry, you need an advanced degree. I think a lot of times when universities invite speakers, they invite speakers that hold certain responsibilities, and most of the time they come with graduate degrees. But at Tokyo Electron, or even at other companies I work with, majority of the workforce are holding bachelor's or master's degrees, and they contribute impactfully to the company itself. Of course, when you come with a graduate degree, you might work on a research development project. But for example, at Tokyo Electron, in the largest development center we do have a lot of bachelor's degree joining us. And after several years of experience, that is equivalent to a master's or even a PhD degree. So I really think it's a misconception that the semiconductor industry needs graduate degrees. I think a bachelor's degree is sufficient as long as you have the motivation, you're really passionate about the technology, and that will really bring you far. And a graduate degree is just, you're interested, you stayed in school much longer than some of your peers. That's the main difference, I think. Yeah.
Thank you.
I had one last question. So With your internship program, what is the main objective for your undergraduate and graduate interns?
Okay.
And what kind of projects do you have them working on?
That's a good question. So for the graduate students, we typically have a very well-defined project for them because they already have background information on the semiconductor industry or the specific projects we worked on. A lot of times the graduate students that join our labs here at Tokyo Electron, they are professors that we have a joint development project working on. We know the graduate students and then we bring them in to continue working on a particular problem. For undergraduate degrees, it's twofold. Of course, they come work with us, we get to know them, we are really interested to hire them into the company itself. But the other thing is, we understand without you, there would not be us. So a lot of time is, spending time developing your interests. At Tokyo Electron, the internship program is very structured. You will go through a lot of different courses, introduce you to the semiconductor industry, the supply chain, the different technologies. For example, I show you the whole manufacturing process, right? There will be lectures on what is deposition, what are the different concepts of deposition, what is the etch. So it's really, I would call it a summer program to give you more information about the industry. And then a lot of times the interns would have roundtables with our executives right up to the president to answer your questions, why the semiconductor industry, what does Tokyo Electron do. So in short, graduate students are more a defined project, we have worked with them. Bachelor's or master's students just come in to work on a variety of projects because the intention of is really to learn about you and you learning about us, vice versa.
So I think one last question. We have a question about your cryogenic etching technology to try and improve the energy efficiency of semiconductors. And any other innovations in any other areas that TEL's providing to advance the kind of green agenda?
If I have to list the number of innovations, we're not going to get home. So the cryogenic is definitely a big one that we are really proud of in terms of sustainability efforts. And I think one of the things we are trying to do now, because we are a process technology company, and you could see a lot of times we are dealing with different chemistries. So we are starting from ground up when we are selecting our chemistry. We are trying to select more sustainable chemistry that there are not PFAS or chemistries that doesn't have a global warming potential. So these are some of the things that we do behind the scenes itself. In terms of technology, you could see there's a lot of digitization of the technology. We're trying to automate everything that would save on a lot of energy requirements and things like that to promote sustainability.
Well, I think everyone, if we can thank Rhinos for his time.
Thank you.